Welcome back. In our previous sessions, we performed several important measurements using half-wave and full-wave rectifier circuits. Today, we will learn how to model and simulate a 12 volts battery charger in MATLAB Simulink, using a full-wave bridge rectifier and a step-down transformer. Problem statement. Objective. Design and simulate a battery charger system in MATLAB Simulink, using a full-wave bridge rectifier and a transformer to step down the 220 volts RMS AC mains voltage. The system should safely and effectively charge a 12 volts, 50 ampere hours lead-acid battery. System requirements. AC supply parameters. Input voltage, 220 volts RMS. Frequency, 50 Hertz. Transformer. Type, step down. Purpose, to match the required DC voltage after rectification and filtering. Rectifier type. Full-wave bridge rectifier using 4 diodes. Consider diode forward voltage drops, each of 0.7 volts. LC filter. Design and implement an LC filter to smooth the DC output. Battery specifications. Type, lead-acid. Nominal voltage, 12 volts. Capacity, 50 ampere hours. Charging current, between 10 and 20 amperes. Initial state of charge, 50%. Simulation requirements. Output voltage after filtering, around 14 volts, but not less than 13 volts. Charging current, between 10 and 20 amperes. Ripple voltage, peak to peak, must be less than or equal to 0.3 volts peak to peak. The simulation should run for at least 20 to 30 seconds to achieve steady-state response. Use scopes and measurement blocks to record. Output voltage. State of charge of the battery. Charging current. Getting started. Let's begin. First, launch Simulink by clicking the Simulink icon in the toolbar. Click on Blank Model to open a new blank model. Now, let us save the model. Click the Save icon. Give your model a suitable name. And then click Save. Add the required blocks. Let's add blocks to the model. Open the library browser. Go to Simscape, then Electrical, then a specialized power system, and then click on Sources. Right-click on the AC voltage source and select Add to the model. Also add the battery block into your model. Next, go to Power Electronics and add a diode block. Then, go to Power Grid Elements and add a linear transformer block into your model. Then, go to Passives and add a series or LC branch to your workspace. We will also need a Power GUI block. Let's add it to our workspace. Let's arrange the block to make them ready for connection. Double-click on the AC voltage source to open its settings. As the given RMS voltage is 220 volts. So, the peak voltage for this value is 311 volts. Set the frequency to 50 Hertz. Then click OK. Next, double-click the transformer block. Set the units to SI. Nominal power of the transformer is calculated by using this equation. From Rashid's textbook, the secondary voltage is equal to 1.11 into VDC. Since our desired DC output is 14 volts, therefore, the transformer's secondary voltage is 15.54 volts. Use the upper limit of the output DC current and the rectification ratio to find the secondary current. The upper limit of the charging current is 20 amperes. And we have already discussed the rectification ratio, which is 81% for a full-wave rectifier. Based on these values, the secondary current is calculated as 24.7 amperes. To calculate the VA rating of the transformer, multiply the secondary voltage by the secondary current. This gives us 383.7 volts amperes. However, we will choose a higher value for safety margin, because we are using an LC filter with a large capacitor and inductor, which will draw high power initially, before reaching steady state. So, set the nominal power rating of the transformer to 500 VA. Also, set the frequency to 50 Hz. Set the primary side RMS voltage to 220 volts. Set the primary side resistance to 0.3 ohms. This is just an approximation. The actual resistance depends on the resistivity of the copper wire, its cross-sectional area, and its length. Set the primary winding inductance to 3 mH. This is also an approximation. We have already determined the secondary side voltage, which is 15.54 volts. Enter the value here. Now, let's calculate the secondary winding resistance. Here's the equation. Use the turn ratio in the primary winding resistance to calculate the secondary side resistance. By substituting the values and performing the calculation, you will get 0.0015 ohms. Let's also calculate the secondary winding inductance, which is 1.5 multiplied by 10 raised to the power minus 5 Henry. Disable the 3-winding option by unchecking this box. Click Apply, and then click OK. Now, select the diode block, and press Ctrl+R on the keyboard to rotate it. Then, open the block. Set the forward voltage of the diode to 0.7 volts. Also, uncheck this box to disable the measurement port. Click OK. Since we will need 4 diode blocks, copy and paste the diode block 3 more times. Place the blocks properly. Open the RLC series branch and select L from the drop-down menu. Finally, let's calculate the values of L and C for the LC low-pass filter, to smooth the current and voltage waveforms and to remove spikes. For a full-wave rectifier, the ripple frequency is double the AC source frequency. So, the ripple frequency is 100 Hz. Let's first find the value of C using the ripple approximation formula. The approximate value of C is 0.6 farad. Next, use the filter cutoff frequency formula to find the value of L. I have chosen the cutoff frequency as 10 Hz. You can use any value below 50 Hz. Lowering the cutoff frequency will improve the DC output quality, but it will also increase the size of both the inductor and the capacitor. Using bulk inductors and capacitors in practical circuits is not considered good practice, due to cost, size, and efficiency concerns. By putting the values into the formula and performing the calculation, we get L as 422 microhenry. I'll use a slightly higher value. So, let me set the value of the inductor to 500 microhenry. Now, copy and paste this block, rotate the block, and open it. Next, select C from the drop-down menu. Enter 0.6 as the value of the capacitor and click OK. Let's connect the blocks. Right-click on the battery block and flip it left to right. Connect it across the capacitor. Now, add a bus selector block from the Simulink library. Also add a scope block and a display block. Connect the measurement port of the battery to the bus selector. Open the bus selector. Remove the default signals. And add all the available signals. Click OK. Let's copy and then paste the scope block. Connect each scope to each output of the bus selector. Also, connect a display block at each output of the bus selector. Now, open the battery settings. Select the required type of battery from the drop-down menu. Set the nominal voltage to 12 volts and the rated capacity to 50 ampere hours. Set the initial state of charge of the battery to 50%. Next, click the Apply button and then go to the Discharge tab. Uncheck this box and enter 14.1 volts as the fully charged voltage of the battery. Click Apply and then OK. Open the Power GUI block. Select Discrete as the simulation type and reduce the sample time for better accuracy. Next, increase the simulation time to 30 seconds to allow the system to reach steady-state response. Finally, click Run to start the simulation. Let's have a look at the waveform of the charging current. There are large spikes in the charging current. It is oscillating between 10 and 50 amperes. Let's stop the simulation and add a series inductor to reduce the oscillations in the charging current. Copy the series RLC branch, rotate it, and connect it in series with the battery. Open the block and select RL from the drop-down menu. Use a small damping resistance with the inductor to further suppress current oscillations. Let's calculate the value of the inductor. Use this formula to approximate the value of the series inductor, where delta I is the desired peak-to-peak ripple current. Let me choose the value of delta I as 0.9 amperes. By substituting the values and performing the calculations, we get 3.3 millihenry as the required value of the inductor. Enter this value here and click OK. Click Run again. Let's observe the current waveform. You can see that the current has been smoothened. Don't be confused by the negative sign of the current. This negative value simply indicates that it is charging current, meaning the battery is in the charging state. Now, open the scope to view the voltage waveform. Note that you cannot use the signal statistics tool to find the peak-to-peak voltage value here. It will lead to an incorrect approximation. Signal statistics observes the signal as a whole from start to end, and subtract the maximum value from the minimum value of the waveform, which is not correct. To correctly calculate the peak-to-peak voltage, we will use the moving maximum and moving minimum blocks from the Simulink library. In this case, we will obtain the real-time maximum and real-time minimum values of the voltage. This allows us to accurately determine the peak-to-peak voltage. Let's stop the simulation and add these blocks from the Simulink library. Also add a subtract block from the library. Next, connect the blocks appropriately. Open each block and set the window length to 4000. What does that mean? This means that the maximum and minimum values will be calculated over a time span equal to 4000 sample times. Since the sample time is 5 × 10⁻⁻⁶ seconds, multiplying this by 4000 gives us 20 milliseconds. This is equivalent to the time period of a 50 Hz signal. This setup will give us the maximum and minimum values of the signal over each 20 milliseconds. Let's start the simulation again. The simulation has completed. Now, let's check the results. You can see from the display that the state of charge of the battery has increased to 50.33%. Open the scope to view the graph. Now, check the current waveform. You can see that the charging current, once it reaches steady state, stays within the required range, that is, between 10 and 20 amperes. The voltage is also stable at the desired value. The peak-to-peak ripple voltage is far less than the required limit. You can also confirm this from the display. Summary. In this tutorial, you learned how to model and simulate a 12 volts battery charger in MATLAB Simulink, using a full-wave bridge rectifier and a step-down transformer. Your task. For the same model, increase the charging current to 60 amperes, and build a control system that will connect or disconnect the AC mains supply based on the state of charge of the battery. Also, ensure that the battery does not discharge back through the charger when disconnected from the main supply. Hints. Use a breaker block from the Power Grid Elements section of Simscape Electrical. Connect the breaker in series with the AC voltage source. To control the breaker, monitor the SOC of the battery. Compare it with a constant value of 100, representing full charge. Use a relational operator block to check if SOC is less than 100. Connect the output to the control port of the breaker. To prevent battery discharge through the charger when the AC supply is disconnected, consider adding a diode between the charger and the battery. Thank you for joining us.